Ladies and gentlemen, it is my greatest pleasure to welcome you to the second keynote of the day. My name is Jędrzej Potoniec and I'll be chairing this session. Before we begin, a few technical remarks. The talk will take about 15 minutes and then we'll have around 10 minutes for live questions. Please ask your questions during the talk in the Q&A tab in the conference app. And the keynote will be given by Dr. Stanisław Woźniak, who pursues his research in the field of neuromorphic computing, taking inspiration from the neural networks in the brain to develop novel computing architectures. He received his PhD in 2017, and in 2018 he received the Fritz Kutter Award of ETH Zurich and IBM Research Division Award for his contributions in neuromorphic computing using phase change memory devices. Since 2018, he is a postdoctoral researcher at IBM Research Zurich. His current focus is on closing the gap between the theoretical appealing properties of spiking neural networks and their applications. Stanisław, the floor is yours.
Hello, my name is Stan Woźniak. I work at IBM Research Zurich. It's a pleasure for me to be able to present to you our work on brain-inspired computing. In this presentation, I'll first discuss what IBM and IBM Research are, and then we will go into neuromorphic computing, which takes inspiration from neural structure, neural dynamics, and neuroplasticity to develop novel architectures for the computing systems and novel approaches to AI. IBM is an enterprise technology company driven by the expertise of hundreds of thousands of IBMers all around the world. It is built on trust and responsible stewardship of technology. We are number one in many business critical areas, including AI for business and hybrid cloud. We are also number one in very innovative areas, such as quantum computing and blockchain. IBM Research is a research division of IBM that employs more than 3,000 researchers in 19 locations. One of them is IBM Research Zurich, that was established in 1956, and it is renowned for its world-class scientists, and including the works of on scanning tunneling microscope or on high-temperature superconductivity, for which our employees received 2 Nobel Prizes. IBM Research conducts research in various disciplines, ranging from artificial intelligence, blockchain, quantum computing, IoT, up to semiconductor technology, biology, physical sciences. We are behind the first and the second top supercomputers in the world. And if you want to know more about our activities in various domains, please follow us on Twitter. One of the areas of our research is neuromorphic computing. It is taking inspiration from the brain in order to develop new computing architectures and better AI systems. If you look at today's systems, for example, IBM Watson, we can build astonishing machines that can compete with humans on cognitive tasks, such as playing the Jeopardy game. But it comes at a huge computational cost. Behind Watson, there is an entire data center that takes 80 kilowatts. And it needs these 80 kilowatts to compute with the brains of the human that consume around 20 watts. So there is a large gap between what we achieve today with the computers and what the brain achieves. One of the reasons behind this is that current computing systems rely on so-called von Neumann computing architecture. In this architecture, the compute and the memory units are physically separated, connected via bus that has limited bandwidth. And also this design inherently involves juggling the data back and forth between the computing and the memory unit. If you look at the brain and you take the inspiration starting from the neural structure, so the substrate of the brain, you immediately find ideas how to overcome this von Neumann bottleneck and decrease the power consumption. Furthermore, if you look into the neural dynamics, so how the neurons operate in the brain, you can take further biological inspiration to enhance our AI systems. Finally, the brain can learn through neuroplasticity. It can adapt by learning from experience. And we can take some of the insights on how the learning is happening in the brain to develop new seamless online learning algorithms. So let's begin with a little bit of history on neural networks modeling. It was in 1906 when Ramon A. Cajal has received the Nobel Prize for his descriptions of the structure of the nervous system. Through his works, we understood that the brain comprises neurons interconnected by synapses. Based on these works, many researchers started creating models of the neurons and of the neural networks. In 1943, McCulloch and Pitts presented the so-called artificial neuron model. In this model, the weighted sum of the inputs is then processed by a nonlinear activation function and produces an output. And this kind of model takes a very remote inspiration on the structure of the neuron that comprises synapses at the dendrites and emits outputs from its axons. This model has then been developed into a multi-layer artificial neural network, and combined with backpropagation and fast computing machines, it led to so-called deep learning revolution. The artificial neural networks, as a part of machine learning, are the foundations of the modern deep learning systems. However, in parallel to these works, neuroscientists continue to try to understand the dynamics of the biological neurons. In 1952, Hodgkin and Huxley received the Nobel Prize for their description of the neural dynamics. This dynamics has led to so-called spiking neuron model, a biologically plausible abstraction of the dynamics of the biological neurons. Having learned about the spiking neural networks, John von Neumann, the father of the computer architecture, has postulated to create new SNN-based brain-inspired architectures for the new class of computers, but unfortunately he passed away and couldn't continue his work. In the 1980s, the idea was revived at Caltech, and from that period, many interesting works appeared, including the IBM True North chip. This led to a field called neuromorphic computing, for which the basic model is the spiking neural network, or SNN. And the idea here is to emulate the dynamics of the biological neurons, considering a very low level, very intricate level of the biological detail. Both of these approaches have been developing kind of separately, and they have their own advantages and disadvantages. And in this talk, we will also discuss how we can actually combine, how we can bridge these two avenues of research to combine some of their advantages. But let's start with the neural structure of the biological neurons. Biological neurons communicate using spikes of voltage that when appear, they convey a value of 1. And when they do not appear, this means that no value is transmitted. So this corresponds to a value of 0. The biological neurons use in this way, in consequence, digital communication, like computers, which is reliable, considering the very noisy, wet environment of the biological neurons in the brain. And it's also very efficient because they use sparse communication. Most of the time, the neurons remain silent, and just occasionally they send these spikes. So this is a very efficient way of communicating. These spikes arrive at the dendrites of the neurons, and they are weighted by synaptic weights. This information is then integrated into the cell soma that performs an analog stateful computation utilizing physical phenomena in the neuron. This is relatively reliable. The analog computation is reliable only when it's relatively local and confined to a small volume, which is the case of tiny biological neurons. And it's also very efficient because here we have dense computation. So at each moment in time, continuously, some value is stored here and it evolves over time. And for this kind of computation, this analog computation is very efficient. Then, based on the results of this computation, output spikes are emitted through the axons down to the next layers of neurons. How we can take inspiration from this to build neuromorphic computing systems? First, let's look at the synapses. The biological synapse is around 2000 nanometer wide. Here you have the synapse. And the synapse uses the sodium and potassium ions to communicate through the ion channels in the cell membrane. The synapses are characterized by conductance G with a resolution of around 4 to 5 bits. The question is, can we find something similar in nanotechnology to implement such synapses? The answer is yes. Very interesting novel technology is so-called phase change memory devices. These devices, they are very tiny. So here you can see it's around 150 nanometer in size. Here you have 1-to-1 scale picture. And they are also characterized by conductance with a resolution of around 4 bits. So this is quite similar to the biological synapses. But here they use different carriers, so they use electrons directly. By the way, you can also manufacture them to be smaller than this. You can then use these phase change memory devices to store memories and to modulate the input currents, similarly to the biological synapses. You can arrange these phase change memory devices, and we typically do this in the form of a 2D crossbar structure, where each row corresponds to an input line, so to a particular input stream, and each column corresponds to a neuron. At the intersections, you have these phase change memory devices that are the synapses of a particular neuron. This approach is CMOS compatible. This means you can easily manufacture this using existing processes of chip manufacturing. And it takes inspiration from what we've described about the biological neurons. So the basic neuronal operation, which is vector multiplication on a level of a neuron, but vector and matrix multiplication if you consider an entire layer of neurons. So this operation, a weighted sum, can be computed using physical properties of the crossbar, similar to being computed using physical properties of the biological neurons. So here you just use Kirchhoff's law in the analog domain, and through this you can compute all of the somatic inputs in O1 time. So this speeds up considerably the computation. You can also use these phase change devices in order to implement some of the dynamics of the soma, so the internal part of the neuron. And this kind of implementation can exhibit very similar properties to biological neurons. So how does phase change synapse, how does a phase change device work is that it comprises of phase change material between the top and the bottom electrode. And this phase change material can be in an ordered crystalline phase or in a disordered amorphous phase. The ordered phase, so the crystalline phase, has high conductance, and this amorphous phase has low conductance. And the relative configuration of these two phases determines the conductance of the entire phase change memory cell. You can change this conductance by applying programming pulses and inducing phase transitions. What is interesting, this process can be accumulative. This means that you don't need to know to which value you program the device, or you don't need to read the device first. You can just use it to accumulate some information by sending accumulative pulses. The advantages over conventional memory are that it is a multi-level device in a single physical nano device. So instead of having multiple transistors to implement a register, you just have a single nano device that is a multi-level device. It is non-volatile because this configuration remains even if you power off the whole system. Therefore, it can be very low power. Also, the conductance of the memoristic devices, so this configuration, is adjusted by modulating the currents that are flowing through such a device, which bears some resemblance to how learning in the biological neuron occurs, where there are activities around the synapses that actually cause the synaptic weight to be adjusted in the process of neuroplasticity. And here we implemented a very simple neuroplasticity rule called STDP that, based on the activities at the inputs and the activities at the outputs, applies accumulative pulses to these synapses. This is a single neuron that is entirely implemented using phase change devices. We were able to show that this kind of a neuron can learn spatio-temporal correlations in the input streams. It extracts kind of the first principal component of what it sees at the output in an unsupervised way. We have shown that you can determine correlated input streams among 1 million inputs, even if these streams have a correlation coefficient as low as 0.2. And this is an important computational primitive that you can use for many tasks. For example, if you couple a set of such neurons together with a biologically inspired mechanism of lateral inhibition, you can present various inputs to such a network, and it will learn them in an unsupervised manner. So, for example, here what we do is we present the MNIS digits without presenting the labels. So this is unsupervised learning. And then these neurons, they learn the templates of these digits. Here you have the weights that were read from the phase change devices in the prototype chip. And afterwards, you assess to which inputs these neurons are most actively responding. And in this way, then you can use them for the classification task. If you furthermore expand these neurons with additional feedback mechanisms, also taking inspiration from the biology, you can induce them to learn features, to extract features of the inputs you present. Here on the left, you have very simple data set of 3 images, and for these images, the network can extract various kinds of features depending on how you configure this feedback. Can be similar to principal component analysis or independent component analysis or matrix factorization. or also features extracted by autoencoders or restricted Boltzmann machines. Again, these images here that you see, they were obtained in a prototype phase change based chip that you see here on the right. To sum up, the inspiration on the structural level can lead to very interesting new kinds of hardware. For example, we discussed this using the phase change memory-based hardware examples, which operates using a different principle than the classic von Neumann machines. It stores everything in the phase change devices, so it stores the operands in the it stores the memories in the phase change devices, and there are no transfers between memory and CPU. So the system design directly corresponds to this neural network, and it's highly parallel. You can accelerate through inherent physical properties the basic operation of the vector matrix multiplication to execute it in O1 time. And this is similar to how the biological neurons use their physical structure in order to perform the computation. Furthermore, it's low power because we use non-volatile memory elements. And it leads to very interesting gains, which are we are able to build faster and smaller synapses than the one from the biological substrate. And it is orders of magnitude faster if you want to run such a system versus if you want to, for example, simulate such a neuromorphic system. The applications we've demonstrated are basic unsupervised learning problems. But now the question is, okay, this looks very appealing, but we would like to solve more challenging problems, such as the ones that are solved by the modern deep learning. So in order to achieve this, we need to look a little bit more into the neural dynamics and how we can actually make use of it and how to train it to solve more complicated problems. The biological neurons operate using this differential equation. So they possess a state variable called membrane potential, VM, that decays with a time constant tau, and also integrates new inputs or new insights from the dendritic currents marked here with I. When the state variable crosses a particular threshold called spiking threshold, VTH, an output spike is emitted on the axon, and the state variable is being reset. So we propose to formulate this dynamics in a way that you can also run it in deep learning systems. We describe this differential equation using these two state equations here. And what we obtain is so-called spiking neural unit, where the first subpart of this unit performs the accumulation, so performs the integration, and the second part performs the spiking. So it checks whether the threshold has been crossed. If the threshold has been crossed, we use a step function activation function. So this unit emits either zeros or ones that corresponds to no spike or spike. And when it emits 1, then it activates a reset gate that resets the state variable to 0. Through this formulation, we are able to bridge the spiking neural networks with the artificial neural networks and make use of the deep learning frameworks, training routines, and data sets. And simultaneously, what we can achieve is we incorporate new kind of dynamics that is qualitatively different than what is present in current deep learning, but it is brain-inspired. Here you see a plot of the response of the of the state variable of the neuron, so the membrane potential, the spiking neuron. You can see how on inputs, on receiving inputs, it integrates these inputs, and then you also observe the membrane potential decay. When the threshold value is crossed, a spike is emitted, and the value of the state is being reset. This is a plot of the SNU implemented in TensorFlow. You can get the implementation from our supplementary material that is referenced here. And as you can see, the dynamics of what we have implemented in SNU aligns with neuroscientific simulation frameworks, for example, Brian-2. Furthermore, what we can do is we can also change the activation function from a step function to a sigmoid function. And then SNU becomes a very interesting novel unit in which the inputs and outputs are operating in floating points, so similarly as in artificial neural networks. But the internal dynamics has the resemblance of the biological neurons. We call this approach soft SNU or SSNU. The advantage of formulating spiking neurons in form of SNUs is that we can directly reuse the training routines from deep learning frameworks. Here you can see, for example, an unrolled SNU unit when it is being trained with the backpropagation-through-time approach. So backpropagation-through-time is a common approach to training temporal units that have some form of recurrency, such as this connection here. And what it does, it unrolls the network, copies this over multiple time steps, and then propagates the gradient back in time, back to the original inputs, and adjusts the weights automatically. In comparison to other common temporal ANN units, the SNU has the lowest number of parameters. And this translates to being the most efficient temporal unit. If you run it, for example, on MNIST, then and use a CPU, the wall time of a LSTM is 8 times longer than of a network based on an SNU. Furthermore, it has the advantage that you can directly transfer the weights that you obtained through this training and deep learning frameworks to the neuromorphic hardware to further accelerate your computation and to achieve very low power solution. The parameters can be mapped one-to-one because our formulation retains direct compatibility with the canonical leaking integrated fire model. From the deep learning perspective, the SNU provides different unique dynamics, which you can make use of to solve some of the interesting problems. Applications include both SNN applications and ANN applications, because right now this unit is kind of simultaneously an SNN and an ANN. We start from the very classic data set for the neuromorphic computing, which is MNIST, but with rate-coded inputs. It's a temporal version of MNIST that encodes the grayscale values of the MNIST images in form of spikes. So you get input spikes for particular pixels, and the brighter the pixel is, the higher the frequency of these spikes. These spikes are randomly drawn from a Poisson distribution, and they are fed into the spiking network. What we have done is we have actually fed them into various units. So in all cases, the architectures are the same, but we varied the units that were used for backpropagation through time training. As you can see, for this particular version of MNIST, the spiking neural network and the soft SNU-based implementation performed better than RNNs, LSTMs, and GRUs. What is also very nice is that the spiking neural networks were scaling well with increasing depth. So through the application of this principle, we were able to kind of jointly optimize the entire system and get some benefits from increasing the depth. Furthermore, we have also presented the convolutional spiking neural network in the sense that the convolutions now are tied to the soma of biologically inspired neuron, and the convolutions become temporal components. With this approach of temporal stateful convolutions and a deep SNU or spiking neural network based on the SNUs, we're able to achieve the record SNN accuracy for the great coded MNIST dataset. When it comes to the deep learning datasets, we started from language modeling on the Pentry Bank dataset, where for standard non-regularized word level models, we got a pretty decent perplexity. With the music prediction on Johann Sebastian Bach dataset, we were able, with the spiking network, to almost reach the LSTM accuracy, and with the soft SNU to surpass the LSTM and GRU accuracy. With the weather prediction dataset Vienna, we were able to get better accuracy of the soft SNUs than of GRUs or LSTMs. Finally, because of this one-to-one correspondence to the hardware, the SNU enables a scheme that we call training with hardware in the loop. What it is, we use the neuromorphic architecture with phase change synapses in the forward pass. So we run the neuromorphic system, and then we use the SNU running in TensorFlow to get the weight updates. And these weight updates are sent into the neuromorphic hardware to adopt the phase change based weights. With this approach, as you can see here, we were able to obtain better accuracy than with standard weight cloning. So if you train your system in software and then try to program your neuromorphic system by cloning the weights, you get this level of accuracy. But if you perform the in-the-loop training, you actually get better accuracy. This is because that the analog hardware that you use has unique properties, in the sense that the analog devices are kind of unique. They have their own cell variability and drift. And by training with the hardware in the loop, the training procedure somehow recognizes and adapts into the properties of your particular hardware. And in this way, it can provide better training accuracy than if you just clone the weights. So to conclude, we proposed this approach of a spiking neural unit that incorporates biologically realistic dynamics into deep learning. This provides a new perspective that bridges the spiking neural network and artificial neural network worlds. It is the simplest temporal unit, and it enables hardware-in-the-loop training because it provides one-to-one mapping of the spiking neural network model inside deep learning frameworks. And this kind of approach provides best accuracy, for example, for the PCM-based neuromorphic hardware. Finally, let's discuss the neuroplasticity. So the brain seamlessly adjusts the synaptic weights based on the experiences we have. And this is in a stark contrast to what we have just discussed on using SNUs and training them with backpropagation through time. Backpropagation through time provides high accuracy for complex tasks. This is a very strong advantage. And it's also scalable to deep networks, including deep SNNs, through the use of our concept of SNU. But there are fundamental challenges. So let me just play an animation where you can see that your system received some inputs, it produces outputs, but in order to learn, it has to run the backpropagation through time. So it has to unroll backwards in time to calculate what are the errors, and then from these errors to calculate what are the weight adjustments that will be applied to your system. And this raises very important challenges. First of all, it causes system locking during learning, because you run your system forward and then you need to interrupt your normal network operation to execute your learning routine. The memory requirement also for this routine grows with the unroll length. In order to compute all of the values of the errors here and the weight adjustments, you need to store all the past activations. And the longer the sequence you want to train on, the more memory you need to use to store these intermediate values. The solution to this problem is the use of truncated backpropagation through time, or BPTT, where the input time sequence is processed in chunks. For example, you split this input into chunks of 20 time steps, and then you just apply backpropagation on these chunks. But then what happens is that the gradients behind the truncation horizon are ignored. So for example, if you have some input that caused the output more than 20 time steps later, then this will be truncated and the gradient from such an input will be ignored. The consequences are that backpropagation through time is not really biologically plausible. And for the same reasons, it is also difficult to implement in neuromorphic hardware. Because if something is biologically plausible, this also means you can easily implement this using some basic physical substrate. But if it's not biologically plausible, it's quite sophisticated. And this would also mean that the hardware implementation is very complicated. So we really want to have something that would be biologically plausible, not for the sake of being biologically plausible, but because this also simultaneously enables us to have a very simple and efficient hardware implementation. So let's look a little bit into the neuroscientific insights about neuroplasticity. Historically, scientists were thinking that the two-factor learning rules were controlling the synaptic changes, with two factors being the input history and the output history, so the pre and the post-synaptic spikes, so the neural input and the neural output. The most common learning rule of this type is called spike time independent plasticity, and it was actually measured and confirmed in biological neurons in layer 5 pyramidal neurons by Henry Markham in 1997 at EPFL. However, when the same approach was applied in simulations, it did not scale to solving complex problems. The reason for this is that this kind of a learning rule performs separate rather than joint optimization. It's on the neuronal level, not really providing a coherent response on the network level. The current biological insights from the neuroscience suggest that indeed these two factors exist and the measurements were correct, but they form a so-called eligibility trace E that is then afterwards modulated by a third factor, an external learning signal L, which can be the level of a particular neurotransmitter, such as dopamine, serotonin, acetylcholine, noradrenaline, etc. And this approach leads then to joint optimization. Here on the right, you can see an illustration where in green, you have the axons of the neurons delivering spikes to the dendrites of some other neurons. And one of these neurons became active afterwards. You can see then that there is a presynaptic factor and a postsynaptic factor. And this forms an eligibility trace that becomes larger than 0. So For these other neurons, the eligibility traces still remain at 0. And then, when the learning signal comes, the synaptic weight of this synapse, where the eligibility trace is larger than 0, is adjusted, whereas these two then remain at their initial values. So this is the idea of current understanding of the neuroplasticity in the synapses. And we have an idea that we've called OSTL, on Online Spatio-Temporal Learning, in which we try to reformulate the backpropagation through time into a form which would be more similar to these insights on neuroplasticity. So we want to use eligibility traces and learning signals to implement an online version of a learning that would be close to the backpropagation through time. Here in this picture, you see the visualization of the backpropagation through time, where the gray arrows, they correspond to the forward pass, and the red arrows, they correspond to the backward pass of the backpropagation through time. And in OSTL, we first separate the gradients that are flowing over time, so the temporal gradients, into eligibility traces. So here you see, for example, E1, E2 for neuron 1, for neuron 2. And we also separate then the spatial gradients into a form that is similar to the learning signals. So we assume that the eligibility traces will be local in space, and then the spatial gradients should be local in time. If you look at the math, what we begin from is the basic chain rule, and derivation is similar to backpropagation through time, but we factor out it in a form that for each time step, you have the learning signal at this time step t, so this is this LT, and we also want to factor out a form that will be computable locally forward in time, which will correspond to this eligibility trace. In order to do so, we actually need to expand this total derivative, and what we do is we collect here into eligibility vector the terms of this total derivative that are computable via recursion. So the ones that we will be able to compute forward in time. And then we obtain our eligibility trace. And this formulation here, this first part, resembles what we've described in the previous slide on the eligibility traces and learning signals and the neuroplasticity. But we have this additional residual term R. So now it's quite interesting. This residual term can be equal to 0. And in this situation, we get BPTT equivalent gradients, but with a online feed-forward, time-forward formulation. And this is the case for shallow architectures, for which OSTL is then similar to the RTRL from the prior art. But this is also the case for deep architectures encompassing at most one recurrent layer. So for example, when you have a CNN, LSTM, and then softmax on top, you can also get a BPTT equivalent gradients with this online learning approach. There are the approaches that cannot have this R equal to 0. And in these cases, we then typically drop the R term, and we operate with approximate gradients that work astonishingly well. So let's here summarize in an animation what is the difference between the OSTL and the backpropagation through time. Here with the dashed line, you see what were the gradients computed by the backpropagation through time after the backward pass. But now what happens is that as OSTL is executed, it operates forward in time, directly calculating the same gradients that you would get with the backpropagation through time, but this time in an online manner. So you don't have to stop, you don't have to store additional variables of the historic activations, you just continue with your learning. In terms of the complexity of our learning rule, here we have a comparison table. The derivations that we have in the paper have a very favorable O(n)² complexity. It is because of some of the features of the SNNs. So if you apply this to some common spiking neural network architectures, you get very favorable complexity. We also provide in the supplementary notes derivations to for generic RNNs, LSTMs, and GRUs, but the complexity is then higher. We are working on approximations, so this might improve. Okay, so how does this perform? If you apply OSTL on the music prediction dataset, so Johann Sebastian Corrales dataset, this architecture actually has R equals to 0, so you get BPTT equivalent gradients. And you can see this, that results are really the same for backpropagation through time and for OSTL up to numerical rounding. And for other data sets, the situation can change. So for example, here the R is not equal to 0, so here we operate with approximate gradients. And here for this temporal rate-coded MNIST and this simple architecture, we do get some drop. Then, if we operate with the language modeling, so with the entry bank data set, we also get a drop, but a very small one. So the perplexity is quite comparable. Finally, for the speech recognition on the timid data set, for the architecture with a one hidden layer, the OSTL is equivalent to BPTT. But for the two layers, we operate with the approximate gradients, and there we evaluated and compared how OSTL works in comparison to the truncated backpropagation through time with various truncation horizons. And here you can see that the OSTL achieved better result than the truncated backpropagation through time with 50 steps of unrolling into the past. The best performance was achieved by the full backpropagation through time, so full unrolling. But OSTL, with its approximate gradients, because this is the architecture without equivalence, it is situated somewhere between these 50 and 90 unrolling time steps. Okay, so this concludes the discussion on OSTL. OSTL is an online learning algorithm that takes inspiration from neuroscience. It is based on the insights from the neuroplasticity on separation of the spatial and temporal gradients. It is applicable to deep neural networks, into spiking neural networks, but also to artificial neural networks, to their recurrent versions. Depending on the architecture that you use, you can get gradient equivalency to backpropagation through time, or it can operate using approximate gradients. Still, you get relatively competitive accuracy. The advantages are that it's forward in time with unlimited time horizon, and it has constant memory requirements. So potentially it's easier to implement this in hardware. The initial derivation for the SNNs has a complexity of O(n)², which is quite favorable. For LSTMs and GRUs, we are working on making better. But please do have a look into our archive paper here. So to sum up, we've discussed our work on brain-inspired computing, in which we took inspiration from three aspects of the brain. Firstly, we discussed how from the neural structure we can analyze the substrate of the brain and implement the insights into neuromorphic systems, for example, the ones that are based on phase change memories. And we are able to show that through analog and digital computations that follow the principles from the biology to use the physical properties, we are able to accelerate important operations, similarly to how biological neurons just use their physical structure to perform the computation. Then we discussed how the neural dynamics, so the operation of the biological neurons, can be incorporated into deep learning frameworks and can be applied to solving challenging problems in deep learning. The SNU that we used to build this bridge is the simplest powerful temporal neural unit right now that you can use in the deep learning frameworks. Lastly, we discussed the neuroplasticity. So the brain is able to adapt online to what it sees, and the backpropagation through time is not really a solution, in particular for if you want to run your system online and if you want to have hardware that would be able to learn online. And so therefore, we, based on the insights on the synaptic traces and on the eligibility traces and learning signals, we developed the OSTL, which can provide BPTT equivalent online learning solution and can be used to build these new kind of online learning systems. Finally, I would like to thank my collaborators with whom this work would never have been possible. And the parts of the work that were presented here are also funded as a part of a small project, the KISTERA initiative. And on our side, it is funded, this part of the initiative is funded by Swiss National Science Foundation. So with this, I would like to thank you very much for your attention.
Thank you, Stanisław, for your very inspiring and interesting talk. There are many questions from the audience, and the one that is absolutely top voted is the one asked by Ricardo. Is backpropagation a possible or realistic approximation of how the human brain actually learns?
Okay, so thank you for all of these interesting questions. I think that somehow partly we already discussed this in our talk in the last part. So directly it's not really plausible, but there are some aspects of it that actually are probably used by the brain. So for instance, the eligibility traces, they provide some form of implementing the backpropagation through time temporal dynamics, but they also have to be combined with the learning signals L. And for example, what we are doing there in OSTL, we are using the chain rule and we are using the delta rule. So the basic concepts, there are actually foundations of the backpropagation. And these foundations, they are in the brain. But the way how we actually implement the backpropagation and backpropagation through time in our existing networks is not really biologically plausible.
Thank you very much for the comprehensive answer. And Kacper asks do you think that large enough neural network could behave like a human brain? Maybe quantum computers would be able to help us with it.
So I think that there are two aspects here. One is whether just going large would enable us to simulate the human brain. Another thing is the quantum topic. For just building a very, very large network, it won't work. Why? Because the existing, I mean, it also depends. The existing models, if you think about just taking existing models and scaling them up, they won't be able to do what the brain does, simply because the brain actually has different kinds of neurons. What we have discussed here is a very rough abstraction of only one kind of the neuron. a neuron from cerebral cortex. So the brain comprises multiple different parts, and these parts, they were evolutionary, developing at different stages of the evolution. So for example, you have brainstem, you have thalamus, you have hippocampus, you have a cerebellum, you have cerebral cortex, and in all of these parts of the brain, actually the neurons are different. And what we were discussing here, these were the neocortical neurons, so the ones from the outer part of the brain that correspond to abstract reasoning. And these, we already abstracted many of the details by, for example, using the model that we presented. So just simply because the dynamics of the brain is not that, not what we described, we are just making some small steps, and we are just modeling some subparts of the brain. So just sheer lack of encompassing in our model of all of these types of dynamics, we will not be able to reproduce this. And also there are many other open aspects, such as there are people who are claiming that the intelligence must be embodied, so that in order to have your network in your brain to train to perform as humans perform, it has to be exposed to the real environment from which will learn similarly to humans. But if you have a machine and if you just want to simulate something, it would be very difficult to build so. So first of all, the dynamics, we were just simulating a very small part of, I mean, some part of the brain and just some basic rudimentary abstraction. Secondly, the inputs would be very difficult to replicate in a simulation. And thirdly, there are things that actually we do not model and we might even do not know about. And this goes actually to the quantum part of your question. So there are some works that show that the quantum effects are important, for example, in some processes where you have catalysts. And you have some catalysts that are operating in the brain that actually support some biological processes also involved in neuroplasticity. And some people claim that even if we will be able to simulate at a very low level detail, the simulation would have to even include these quantum effects, for example. So quantum is coming there, but this is a very speculative thing. But the answer is no.
Thank you very much. And Dariusz wonders whether the neuromorphic chips, which are energy efficient, if they are also cost efficient in production, assuming that spiking neural networks will be able to mimic artificial neural networks, which would be cheaper to build and train.
So currently, it's all a question of what is the market and what is the volume of the hardware that you need to produce. Currently, the biggest volumes are achieved, for example, for the GPU production. So from that perspective, if we would try to build some kind of a neuromorphic chip, it would be initially difficult to compete with the price, but it all changes with what is the market. Right now, for neuromorphic computing, it is very crucial to come up with a model of a spiking neural network and the approach of training spiking neural networks that would enable to construct these chips in a way that would be then scalable and simultaneously that the accuracy will be high enough. So I would say that currently neuromorphic computing is at the stage that this is all in development. So in recent years, we have made many progress. We have made great progress in terms of improving the accuracy of these systems. The hardware is also actually, there are some prototype chips already available, but we have to plug in all of these things and then see how this dynamics would play a role. But as you have seen in my presentations, in some applications, actually the accuracies that we get right now are better than the ones of the ANNs. In some, actually ANNs are better. It all depends on the types of the tasks that you're running. So there is no clear answer, but definitely there is a huge potential if you would combine everything, because you can just say, okay, I just take the SNN model and I also run it on the GPU. It has an advantage if it can solve your task, this SNN model. For example, it can be just 1/8 of the energy spent on running an LSTM, as we have shown. So if it works for your task, it can already reduce this. But ideally, if you have a comprehensive solution where you have a neuromorphic chip running this SNN model using, for example, online learning with this idea of OSTL, then this is, for example, a true game changer. And then, although, for example, the cost might be a little bit higher because of the use of some special production processes or something, it would still, for example, pay off. So it all depends how it plays out, but it's being shaped now.
Thank you. I believe that the next question from Ricardo is related to this previous one. What would be the benefit of using spanking neural networks instead of artificial neural networks? Is it only a very inspiring research question, or can you think about any revolutionary applications of them?
I would say that the spiking neural network, just the idea of this model, as we have shown, can have less computation, so it's much simpler and can still solve temporal tasks. So for example, it can be a better alternative to LSTMs, but the true game changer is when you consider the entire spectrum of neuromorphic computing. So the dynamics of the SNNs, the biological inspiration of how you actually construct the neuromorphic chips, and also that you change actually the mode of learning into, for example, online learning. So all of this combined, then yeah, this would give you an advantage.
Thank you. Philip asks, whether do you think the spiking neural units can be used to build an effective translator in brain-machine interface? How about using them to enhance communication with existing motorized limb prostheses?
I think in principle, yes. So what our work on the SNUs has shown is that the spiking neurons are quite similar actually to the deep learning neurons. So for a very long time in history, as you have seen this timeline, these two research avenues were completely separate. And it's only recently that the people from the spiking neural network community, who are also neuroscientists, who also analyze these biological signals, they realize that they can actually plug this into the deep learning frameworks. So I would say yes, and this actually also applies to other units. So in theory, what you could try to do is you could try to get the outputs from the spikes into your other kinds of units, for example, RNNs, LSTMs, and to interpret them. But if you would like to send it back to the brain, most probably you have to use units that emit zeros and ones, because this is how the brain communicates. So then, for example, with SNUs, you could really have some advantage.
Thank you. Jasprit is interested if you need any special hardware other than GPUs or CPUs to train spiking neural networks. And if such, is it possible to obtain such a hardware?
The best way to train is currently the easiest way to train is to train through this SNU, and this implementation is available in TensorFlow. You can go to our paper, and it's in the supplementary material in form of a zip file. So the simplest answer is you can use a GPU, and that's perfectly fine. What we are thinking and envisioning is that in the future, we would like to have this implemented in hardware. So for example, existing hardware, IBM TrueNorth chip that runs extremely efficiently the SNNs, it only runs them for the inference. If you want to do their training, still you need to do this somewhere else. But our vision is that we would have to something that will be also possible to train in hardware, and then probably that would be a better solution than a GPU. But currently, I would suggest, yeah, please do use GPUs.
Thank you. It's a very good news, actually, that the simplest way is the preferred way. There are still more questions to be asked, but unfortunately, we are already running 7 minutes behind the schedule. So thank you for your very interesting talk. Thank you all for attending this session and asking so many interesting questions. And please enjoy the rest of the conference.